Hi everybody, Angie Johnson here. Thank you for tuning in. And what I'd like to do today is start by going over some normal distribution problems from our book as well as some probability stuff. And there are a few things that I need to review before we dive into some of the example problems from the book. So kind of like a flipped lesson here. I'm going to go over some of chapter 4 that we've gone over in class. So first thing, we've already talked about this in class, but normal distribution model, you can see two different examples down here. I like to call those the bell-shaped curves, and you can read, formal definitions and what the mean and the standard deviation refer to within here. But for these two graphs, this one is a mean of 0. It's a number right in the middle, and this is a standard deviation of 1. Every single increment to the left and to the right is just 1 unit. And then this bell curve, which looks exactly the same, has a very different mean, which is 19, with a very different standard deviation as well. Each increment here is going by 4. That's a standard deviation of 4. And so just another thing that we've discussed in class to review before I go into some practice problems. What about z-score? So we have talked about z-score before. Here's the formal definition. It is an observation that is the number of standard deviations that falls above or below the mean. So we have positive z-scores and we have negative z-scores. Here's the formula, the x meaning the observed value of whatever it is the test that you're doing, minus the mean, so how far away is the x from the mean, and divided by the standard deviation. So what I was trying to do was figure out what a real-life example could be referring to one of these graphs up here, and I thought that since we're in the middle of soccer tryouts right now, that I could do an example, just kind of make one up that might have to do with the second graph here. And so I was thinking about doing, we had a 2-mile test, and I have Zoe on my freshman soccer team, and we had a 2-mile test, and she ran 2 miles in 17 minutes. And so I kind of wanted to compare her time, 17 minutes, which falls right about here. I wanted to compare her time to the rest of the team. And again, this is just what I'm trying to come up with here. This is not actual observations that I made. But for example, to kind of put some real-life application into this, to calculate Zoe's z-score, and it just happens that her first name starts with a z as well, I'm going to take her score, which was 17, and subtract the mean, which is 19, and divide by the standard deviation, which is 4. And so Zoe's z-score is going to be negative 2 over 4, which is negative 0.5. And so the fact that her z-score is negative means that it falls below the mean. And in this case, my girls would actually want to have a negative z-score if we were calculating them for everybody, because that would mean they finished the 2 miles slightly faster than average. And so in this case, a positive z-score would mean you were a little bit slower because you took more time to finish the 2 miles. But just depending on what the example is and what the problem is that we're analyzing, positive z-scores and negative z-scores could have other applications, obviously. So the first problem I wanted to go through was guided practice 4.2 about ACT scores. I teach an ACT prep class, and so this is a pretty applicable thing to some of my students as well. And we're trying to compute this guy Tom's z-score given his ACT score, which is important, which is a 24, which is not too bad. The mean being 21 and a standard deviation of 5. And so I'm going to practice kind of drawing a lot of these bell shapes as well, and then I'll get into, again, talking about the difference between a negative z-score and a positive z-score and how that applies to this problem, because it's going to be a little bit different than Zoe running the 2 miles that we already did. So I'm going to start by just drawing the bell shape, and we will practice this a lot. And I'm going to put the mean, which is the mean ACT score of 21, right in the middle. And I'm going to go 3 tick marks to the right, each space being worth 5. So this would be 26, this would be 31, and this would be 36. And then 3 tick marks to the left as well, also representing increments of 5. So 16, 11, and 6. So these are representative of all the z-scores that are going to fit into my bell curve here. And Tom's score is a 24. So it's about right here on my line. And so calculating his z-score, I'm going to use the same formula from above, this one that I have. And so his z-score, his value that I observed was 24. And I'm going to subtract that subtract that by the mean, which is 21, standard deviation being 5. So that's going to give me a 3 over 5, which is 0.6. Keep in mind that is a positive z-score, and in this example, A positive z-score would mean probably a good thing, because that means that you scored higher than average on your ACT. And so that's what the difference. I've got Zoe with a negative z-score, meaning she finished the 2 miles faster than the rest of the team or the majority of the team. And I've got Tom now with a z-score of positive 0.6, which means he didn't score way higher than the average, but he did score a little bit higher than average. So well done, Tom. All right, so for 4.1.4, kind of a similar thing, but we have SAT scores. What I'm going to do first with this mean and this standard deviation is I'm going to draw the curve again, and then we're going to apply this, I think, to a later problem that we're going to get to. So the mean goes right in the middle. The mean SAT score, which is scored very differently than the ACT, is 1,500, and the standard deviation is 300. So I'm going to get 1,800, 2,100, 2,400. And then same thing on this side. 3 tick marks to the left, 3 tick marks to the right. I'm going to get 1,200, 900, and 600. So here's my bell-shaped curve, and this is just all the standard deviations, or the standard deviation with all the increments and with the mean right in the middle. And this actually applies to example 4.8 as well. It's the same picture, so I'm going to kind of bounce back and forth. What's the probability that a randomly selected SAT taker scores at least 1630 on the ACT? I'm going to go back up to my picture, and I'm reading that from down here. We're at least 1630 on the ACT. This is kind of the next example. So 1630 would be somewhere in here. And so think about what at least 1630 means. At least 1630 refers to, if I draw a line and cut off all of this area under this curve, 1630 or greater. So that's actually this part of the graph. Anybody that scored 1630 or higher. That means greater than 1630 is what the at least refers to. And so just keep that in mind kind of as we bounce down to example 4.8 again. We're trying to find the probability that a randomly selected SAT taker scores that. And so far, very first thing I'm going to do is I'm going to calculate the z-score. And so I'm going to do the same formula that we used from above. The x value, the observed value, or the value that this problem is applying to, 1630. And then subtract the mean and divide by the standard deviation. So when I do that, that gives me 130 over 300, which gives me a z-score of 0.43. Now this does not answer the question, but this is going to help us answer the question. This is not a probability, this is the z-score. This means that this 1630 scores 0.43 standard deviations above the mean. That's what that positive z-score means. And so it's a little bit tricky, but I actually do have a z-table down here for, I need to zoom out a little bit. I have a z-score of 0.43, and I'm going to try and find that in my table in order to tell me what the area under the curve for that z-score is. And so I'm looking at the table here, and I'm finding 0.4, and it's already highlighted in the book because this was an example that was done in the book, and 0.03. And so that gives me an area of 0.6664. It's highlighted in red. Okay, and so what's hard about this example is that you have to keep in mind that these z-tables, they are measuring the area to the left of the curve, so that's actually this part. And so in order to figure out the red part, which is anybody greater than 1630, what I need to do is subtract that from 1. And so to finally finish off the problem, since that refers to everybody to the left of the observed value, the 1630, what I need to do to find my area, or my percentage, or my proportion, is 1 minus 0.6664 to get the area to the right. And that gives me 0.3336, which means that is the probability that I randomly choose a student that took the SAT and that they get something bigger than 1630 as their score. So it also converts to 33.36%. That is my proportion, or my probability. And so you guys, for my last example, kind of the same kind of thing, dealing with the SAT and the scores as well, but a little bit of a different type of question. This one is asking for what is the percentile. So a lot of times when you take a standardized test like that, you get your score and then you get a piece of information that is you are in the 87th percentile or you are in the 75th percentile. And that means that you're scoring in that higher than that percentage of students overall that took the exam. And so what we have here is Edward, who got a 1400. And so again, I've already drawn the picture to save a little bit of time, but his score of 1400 is about right here. And what I need to do is figure out what percentile he is. And so I think that this means he's going to be less than 50%, because if he got a 1500, that's exactly in the middle of our curve. And so we can assume by using a little bit of common sense that he is somewhere less than 50% in his percentile. And so what we're going to do is, again, I'm going to calculate the z-score. It seems to be what we're doing for every single problem. But I have the z equals the observed value, which is Edward's score of 1400. And I'm subtracting the mean, which is 1500. And I'm going to divide that by the standard deviation, which is 300. This is all still the same numbers and the same problem, just different applications of that first example that we did. And so when I do this, I get negative 100 over 300. Which gives me negative 1/3, which is negative 0.33. And so this is Edward's z-score, and I don't have the appropriate, this is not applied up here. I don't have like negative numbers and stuff. So there's actually another way that you can, without a table, figure out the area underneath the curve here, or trying to figure out Edward scored higher than how many percent, what percentage of the students. And so this is what we're trying to find here, is where did Edward's score cut off compared to everybody else. And so this negative 0.33, a very similar thing that we did earlier. What we're going to do now is I'm going to review how to do that in the calculator. So in the calculator, you're doing the normal CDF. And for your lower bound, I've gotten in the habit of using negative 1000. Some of you have like the ability to do negative infinity. I guess for this problem, you could just type in 0, because think about the lowest score that you could earn on the SAT would be a 0. But my calculator automatically does negative 1000 now. So you can leave it there, you can leave it 0, you can do negative infinity. That part doesn't really matter. What does matter is the upper bound. And we want to stop this shading exactly where Edward's score was. So that was 1400. And then, of course, it's going to ask you for the mean again, which is 1500, and it's going to ask you for the standard deviation, which is 300. And that is going to spit out an area, which is 0.3694. And considering the entire area would just be 1, 0.3694 underneath the curve, that converts into the 37th percentile. And so that's how to review, like doing it in the calculator. If you have a z-score chart that has every single value that you would need for your z-scores, you could use that like we did the previous example, but in this one I wanted to review how to do this in the calculator as well. And so just to bring this whole thing home, keep in mind what this means is if Edward scored in the 37th percentile, that means that he scored higher than 37% of the average test takers. So a couple different applications. One really important thing to keep in mind is that all of these problems are dealing with a normal distribution. And so something that would screw this whole thing up is if you had a skewed distribution, whether it was right or left, or if you had a really small sample size, really small proportion. All of these problems were taken from normal distributions, and that's why we're able to throw z-scores in and calculate, use normal CDFs, use standard deviation, use means, everything else, because these are all normal normal distributions. So just keep that in mind. All this goes out the window if it's not a normal distribution. Thanks for watching, you guys. Have a great rest of your night.